This lesson is about turning graphs of motion into equations of motion, and the end result will be that we have what is called commonly in physics at LN the 5-column chart for equations of motion. And the 5th column will be derived at a later date, but you can see here this is the end product of what we're trying to develop today. And for the rest of the year, you'll be using these equations that are developed from the graphs of motion. You'll be using these equations throughout physics and all of the rest of the disciplines that we examine. The way that we're going to develop these equations are 3 different ways. Either we're going to find an equation for slope, an equation for area, or we're going to combine equations and solve algebraically. There are 4 scenarios that we want to cover today to develop the first 4 columns of the equations of motion chart. The first is that we have an object, the simplest case scenario, an object starting at the origin with constant velocity and 0 acceleration. Then we'll allow the object to start at a position other than 0, so its initial position is not 0. It still has a constant velocity and 0 acceleration. The third and fourth scenarios are that the object starts from rest at the origin with a constant acceleration. And it starts from rest, and the acceleration is a constant value, much like we've been talking about the acceleration of gravity is constant. In the fourth scenario, the object will already be moving at the beginning of the problem, and its initial velocity will not be equal to 0, but acceleration will still be constant. To develop the 5th column, for non-constant acceleration, we're going to have to do a little bit of calculus to make that happen, and we'll do that at a different time. So we'll get started. The first scenario is a graph of something that is at position 0 at time 0, and we call that S sub 0. That's the initial position. That's the position when time is equal to 0. And the graph would look like this. It would look like a line. The thing is moving at a constant velocity. There's no acceleration. And so this could be a bug crawling across the floor at a constant speed, and it started from the origin, and the bug continues to walk at a constant rate. So how can we get equations from this? Well, we already know that the slope of this line is equal to the velocity. So if we could just use the equation for slope, we could develop the equation for velocity. So let's do that. Slope is equal to rise over run. And in this case, the rise is the change in position over the change in time. And both our S initial starting position and our time starting position are 0. So this translates into S minus S sub 0 divided by time, and S sub 0 is equal to 0. So from this we can literally take the slope being equal to the velocity, and we get velocity equals distance divided by time. And we know that to be true. For constant acceleration, if we simply take the distance and divide that by the time, that's how fast we're going. And so if we rearrange this equation now, we can multiply both sides by t, and we get S equals V times t. And so our 2 equations for this scenario will be S equals Vt, V equals distance divided by time, and acceleration equals 0. And those are the 3 equations that you saw in the first column of the 5-column chart. In our next scenario, acceleration is still 0, velocity is constant, but we let the thing start at a position other than 0. In other words, it's not starting at the origin. Okay, the same thing holds true here. Slope is equal to the velocity, which is equal to rise over run. And so if we take a point up here and we come down to here, this part is the rise, this part is the run, and this corresponds to some value of S later in time. and this is the value of s where it started. And so the slope is equal to the velocity, which is equal to s minus s0 divided by the time. And so our first equation here is v equals s minus s sub 0 over t. And if we rearrange this equation by multiplying by time, and solving for s, the position, we have to add an s sub 0 to the other side. We get the initial starting position plus velocity times time equals the new position. And our three equations for this column, column 2, that you saw on the 5-column chart, look like this. Okay, in order for our third scenario to develop the equations here, we have now moved into constant acceleration, which means the graph of position versus time is going to be a parabola. If it were a negative acceleration, the parabola would go this way, but it's a positive acceleration and it goes this way. So we're going to have to go to the velocity versus time graph, which is a line, in order to develop some equations. So the first thing we'll do is let's stick with our idea of slope, and we know that the slope on this kind of a graph is equal to the acceleration. And here the velocity at 0 time is equal to 0 because it starts at the origin. And so we can develop the equation m equals v minus the initial divided by time, and we know that the initial velocity is 0. And this is all equal to the acceleration. So our first equation that we derive here is a acceleration is equal to the velocity times the time. That's our first equation. We can also rearrange this and get an equation for velocity. Velocity, if we multiply both sides by t, we get velocity equals constant acceleration times time. Now, in order to develop a position equation for this, I'm going to go to a new drawing because that's going to involve the area underneath this graph. And since I've already used up this spot, I'm going to make a new graph. But in order to find the change in position, we're going to find the area, and this area is going to turn out to be the area of a triangle. So here we go. Let's take our third case scenario where we start from the origin and we have a constant velocity, and let's find this area which represents delta S. So we're looking for this area of this triangle at some time down the road where we've achieved some sort of velocity that's listed over here. Well, the delta S, or the area underneath this graph, is equal to 1/2 the base times the height. Well, the base is time, and the height is how fast it goes. And so if I write this out, S minus S sub 0 equals 1/2 VT, and we recognize that the thing also starts from the origin, we get S equals 1/2 VT. Well, the problem here is with this equation is that we very rarely know both the position and the velocity and the time all in one location. So we're going to do a little substitution here. We know from the previous slide that we had up here that velocity is equal to acceleration times time. And now by substituting in what velocity is equal to, we get S equals 1/2 AT times T. And when we multiply that all out, we get S equals 1/2 AT squared. Well, that's a good thing, because we know that on this type of position versus time graphs that if we have constant acceleration, we know that that creates a parabolic shape on the graph. And so here we have the position function for constant acceleration of position versus time. There's one more equation that we need to develop here, and that is occasionally we don't have time. We don't know what the time is in the problem. And so we're going to do a little substitution here to show that there is another equation that we can use to eliminate time from the equations. So we're going to use v equals at and s equals 1/2 at squared. And since we don't know what time is, we're going to go ahead and solve time in this equation. So time equals velocity divided by acceleration. And we're going to substitute that value into this equation. And so I get s equals 1/2 times constant acceleration times the quantity v over a squared. Now that's equal to 1/2 a times v squared over a squared. Now one of the a's will cancel out with the a on the bottom, and we now have an equation that's 1/2 v squared divided by a. And now we want to solve this for v. And so I have to move the 2 over to the other side, 2s. I have to move the a over to the other side, 2sa equals v squared. And I'm going to change the order of these, and I can do that because it's multiplication. And the equation now becomes v squared equals 2as. And so as long as we know the constant acceleration and we know how far the thing has traveled, we can then solve for the velocity. So this is our final equation for the third column, v squared equals 2as. And yes, I know you could go ahead and solve this plus or minus the square root of 2as. It's just in physics we like to keep things as simple as possible, and this appears more simple than this. Okay, onward to the fourth scenario. We're going to start off developing the equation for acceleration first, just like we did in the last example, keeping in mind here that we're dealing with constant acceleration. But the difference is the last thing started from rest, and this is already moving when the problem begins. So instead of this velocity, this initial velocity at time 0 being at the origin, it's up the y-axis just a little bit. In other words, we have a y-intercept in this graph. And so let's go ahead and do slope is equal to acceleration. And the slope now, we can't ignore the initial velocity because it's something other than 0. And so out to the side here, I will draw this. Acceleration is equal to the change in velocity over the change in time. And there's our first equation. Now we can get one more equation from this because acceleration equals v minus v0 divided by t, and typically we know the starting velocity, so we could find a velocity at some time later by rearranging this equation. Excuse me, and we're going to multiply both sides by t, and so I get a times t equals v minus v0, and rearranging this to solve for v, we get v equals v0 plus a t. And if we know the initial position, the initial velocity of an object at time 0, we know the constant acceleration, and we know how long it's been traveling, we can determine what the velocity is. And now once again, to develop a change in position, we're going to have to take the area underneath this. And so I'm going to redraw this. We're going to have to look at what kind of a shape we have here. This is time. And so if I close this off, and I'm looking to take the area underneath this, there are two components. There's the triangle part, which is we're going to get the area of this by 1/2 base times height. And here we're going to get length times width. Okay? So to find the area of this, the area is equal to the change in position, but keeping in mind we're starting from the origin, so S sub 0 is 0, so this is really just S. This is going to be the length times the width plus 1/2 base times the height. Now we want to get these into expressions that come from the graph. So S is equal to the bottom part, the length here is V sub 0, and the width is the time, so we have V0 times time, that's length times width, plus 1/2 the base times the height, so 1/2 base times height. The height is some value V minus V sub 0 times the time. Now, if you remember, we had an equation V equals V sub 0 plus AT that we had already developed. That was back here. If I were to solve this so that I have V minus V0 equals AT, now I could substitute V minus V0 for values that we know. Okay, so this V minus V0 is equal to A times T, and that comes from this equation that we developed right here. So now S equals V0T plus 1/2 AT times T, and once again we can combine the T's and we get an equation that says S equals V0T plus 1/2 AT squared. And that's our position function for an object that travels at a constant speed and is already moving at the beginning of the problem. This is the position function. And once again, this is a parabola based on the fact that t is squared. Now, I would like to say something else. There's one more equation we can develop. In fact, I would offer some extra credit if you would derive this equation. Because once again, we need an equation sometimes that has no time in it, and we need to find a way to take S equals V0t plus 1/2 AT squared, and V equals V sub 0 plus AT. We need to find a way to solve for time and substitute it into this equation. Solving that equation for time and getting an equation that does not involve time because we substitute it out. And so I'm going to give you the result. The result is similar to the one we developed in the third column, which is V squared equals V0 squared plus 2AS. And this is the equation we use if we don't have a time involved in the problem, but rather we can use distance and the initial velocity to find a velocity at a later time. So I'm offering extra credit if you submit this to me, your proof, by solving this equation for time, the second equation right here, solve for that time, substitute creatively into this equation, and get it the end result to show that V squared equals V0 squared plus 2AS. Okay, we've accomplished what we set out to do, which was to derive the 5-column chart, the first 4 columns, keeping in mind that we'll spend a little bit of time developing a 5th column where acceleration does not have to be constant. Now, it's amazing how much of physics uses these equations. You'll be using these all the way right to the end of the year. If there's no acceleration, you want to be thinking columns 1 or 2, and if there's constant acceleration like at the surface of the Earth, these are the equations that will allow you to solve problems. I would like to say that you have now the 7-step problem-solving method, and each time you solve equations using the 5-column chart, you need to use these 7 steps without fail. Follow them exactly. I'm not going to read them to you. And then you can begin working on this very classic worksheet that's been at Lawrence North for at least 25 years, working through each problem, deciding which column you need to be in, selecting the proper equation, solving for the proper variable, substituting in the number with all the units, and so forth. In fact, the test over equations of motion will look a lot like these problems that you see here. So good luck.